by now you've probably figured out that when it comes to looking at rotational motion, it's just a matter of replacing the variables in all of our basic physics equations with the variables for rotational motion as opposed to translational motion. And if you've guessed that, then you're right. So here we could look at translational kinetic energy, or linear kinetic energy, and we know that that's 1/2 mv squared. For rotational motion, you're going to get an analogous equation just by replacing the variables so that we can have actual rotational motion. So when we replace translational variables with rotational variables, we replace mass with moment of inertia, and we'll replace linear velocity for rotational velocity, so that the rotational kinetic energy is 1/2 moment of inertia times rotational velocity squared, and that is analogous to 1/2 mv squared. And it actually makes a lot of sense, and we can prove that this is true. Remember, we have the relationship between, and remember also, like when I say we can prove it's true, we are looking at something that, like, we've collected enough data to know that these laws actually work. Our conservation laws actually are true. Newton's laws for dynamics are true. So we know that the connection between linear and translational velocity is v equals r omega. And so we can do some replacing. We know that kinetic energy is for every particle in a spinning object, right? So we can't just consider one particle. If you've got a disk and it's spinning in a circle, we have to do this for every single particle in the disk. So that means that we'd have to calculate 1/2 mv squared for every single particle. So it would be the sum of 1/2 mv squareds for all of the particles in the disk. Well, for our v squared, I'm going to replace in rw and square it, so then I'd get the sum of 1/2 mr squared omega squared. And if I do just a little bit of factoring to work for my favor, the sum of all the 1/2 is going to be the product of 1/2 times the sum. And I factored out mr squared from my omega squared. And the reason I did that is sum mr squared, well, that's defined, sum mr squared, as moment of inertia. So that means that instead of having to calculate the kinetic energy for every single particle, I'm going to just be able to use the moment of inertia for that shape. So that means that rotational kinetic energy is actually equal to 1/2 I omega squared. So boom, we were able to show that just replacing our linear values with our rotational values actually did give us the equation for the rotational kinetic energy of any object. And since it's an energy, our units are still joules. Nothing's changed there. So let's think about this practically now. An object that rotates around its axis while its center of motion is undergoing translational motion is going to have two types of kinetic energy, rotational and translational kinetic energy. So that means that if you have an object like a wheel, right, that wheel travels from point A to point B. But when that wheel travels from point A to point B, it also rotates. If it's moving with linear motion, it will have linear kinetic energy, 1/2 mv squared. If it's rotating, then it will also have rotational kinetic energy, 1/2 I omega squared. So that means that any object that does both things will have both types of kinetic energy. And that's displayed in this equation here as 1/2 mv squared, and the v is for the object's center of mass, and 1/2 I cm omega squared. All right, and here the cm and the cm here. All right, vcm is the translational velocity of the center of mass, because we can reduce all linear motion so that it's the equivalent of it happening at the center of mass. And ICM is the moment of inertia about the axis of rotation. So that means that wherever it's rotating is going to be this same place here, and so we want to find the moment of inertia around that axis of rotation. And the capital M here is for the total mass of the object, because remember, every single particle has kinetic energy, so that means that we would have to find the total linear kinetic energy of all of those particles and the total rotational energy of all of those particles. So let's go ahead and let's take a look at how that calculation applies to moving, rotating objects. So here we're going to be looking at a sphere rolling down a hill. And since that sphere rolling down the hill is actually getting displaced from here down to here, that means that it's going to have translational motion. And since that sphere is rolling down the hill, it's going to have rotational energy. So we're actually going to be analyzing a situation that has both translational and rotational kinetic energy. And the question is, what's the speed of the solid sphere when it reaches the bottom? So we want to know what the velocity is down here. We know that it starts from rest, so our initial velocity is 0, and our initial rotational velocity is also going to be 0. It's rolling down from a height h, and we're rolling without slipping, so there's no sliding, no work is getting done on this situation. We're going to assume that it's rolling without slipping, so there's plenty of static friction, but static friction doesn't do work, so that means that we're going to be able to use a conservation of mechanical energy law, and we're going to be able to use our new type of kinetic energy to figure out the new final velocity. We're going to compare it to a situation where instead of rolling down the hill, it just slipped down the hill frictionlessly. So it's rolling without slipping. There is no kinetic friction, so no work is getting done on this system. So we have conservation of mechanical energy, which means the energy at point 1 is going to be equal to the energy at point 2. At point 1, there's no kinetic energy, so we've got mgh for the potential energy of this object at point 1. And that's going to be equal to the energy at point 2. At the bottom of the hill, we have displaced completely down to the bottom of the hill, so the potential energy is going to be 0 from our reference point, and it's going to have both translational and rotational kinetic energy, so that means we have 1/2 mv squared and 1/2 I omega squared. And so we're going to have to be able to find both of those values. A couple of things to know is we're not going to be calculating the moment of inertia. It is a solid sphere, so our moment of inertia is given as 2/5 mr squared. So let's go ahead and let's take a look at this. At the beginning, you have mgh. That's totally valid for both linear and translational motion. And then I'm going to plug in for my I, I'm going to plug in my actual moment of inertia. So mgh equals 1/2 mv squared plus 1/2 times 2/5 mr squared. And then for my omega here, since I want my final speed at the end, I'm going to use my my equation v equals r omega, and I'm going to rearrange that to solve for omega. Omega equals v over r. So v over r, and that's a square value. I'm going to go ahead and I'm going to clean this up a little bit. mgh equals 1/2 mv squared plus 2/10 mr squared times v squared over r squared. And now I'm going to do even more cleanup. I can eliminate mass, so the mass of the object was not a critical issue. I can eliminate the radius, and I get that GH equals 1/2 v squared plus, I'm going to reduce that, 1/5 v squared. So 1/2 and 1/5, GH so that's going to be 5/10, 6/10, 7/10, 7/10 v squared. I solve that for v. V equals the square root of 10/7 GH. And that's at the bottom with rolling. So now we have to compare this to a situation where it slid instead of rolling. In that situation, mgh equals 1/2 mv squared, where we can eliminate the masses, and without rolling, v is going to equal square root of 2gh. And so you can see that this velocity right here is the larger velocity. Alright, so that means that objects that slide instead of roll down a hill have a higher linear velocity than objects that roll down a hill. And the reason is that some of the potential energy for objects that roll gets translated into rotational kinetic energy, whereas a sliding object, all of the object's energy gets converted into linear kinetic energy. And so that should make sense. This is also interesting because we can see here that we were able to show that the speed at the bottom of the hill was independent of the sphere's mass and of its radius. So that means that this is going to be true, that the linear velocity for rolling objects will always be less than the linear velocity for sliding objects, always when no work is done, regardless of the shape and distribution of the mass of an object. So that brings us to another question that we could look at. It's a conceptual question of who's the fastest. So if you had the following objects rolling down a hill, and we're going to be taking a peek at what their moments of inertia are. A thin hoop, I equals mr squared. A sphere, I equals, is it 2/5 or 5/2? Sphere, 2/5 mr squared. A solid cylinder, I equals 1/2 mr squared. And an empty cylinder is going to be I equals 1/2 m r1 squared plus r2 squared. And a box, which does not roll, so there is no I. And so we're going to say which one, if they're all released at the same time from the same height, which one makes it down to the bottom the fastest. And we know that if it's frictionless or kinetic frictionless, then E1 equals E2, conservation of mechanical energy. At the beginning, it's just for all of them mgh, and that will equal 1/2 mv squared plus 1/2 I omega squared. We were able to show in the example right before this that we could, it's the mass and the radius, or the distribution of the mass, are negligible values. So the first thing that we could say is that an object with the greatest linear velocity, an object with the largest linear velocity, is going to make it to the bottom the fastest. And that object is an object whose value for rotational motion is 0. So that means that the box will be first. And then, going from fastest to slowest, we now want to look at the moments of inertia for all of the objects. All right, the sliding box is the fastest because it has no rotational kinetic energy, but the rolling objects all have rotational kinetic energy, so they're all going to be rolling slower. For all of the rolling objects, the moment of inertia is going to be the thing that will determine which objects makes it down the fastest. So that means that we're going to have to look and compare those moments of inertia. The hoop, with all of its mass concentrated at the radius, has the largest moment of inertia, so it's going to have the lowest speed, because the largest moment of inertia plugged in there is going to give it the largest rotational kinetic energy, and that will give it the slowest linear kinetic energy. So that means that the hoop is going to be the slowest, and then the empty can, and then the solid cylinder, and then the sphere, and then the box. So that makes the box the fastest, then the solid sphere, then the solid cylinder, then the empty cylinder, and then the hoop is going to be the slowest. And that's because in increasing value, this has largest I, and this has smallest, which means that this is going to have the largest kinetic energy for rotation, and this one is going to have the smallest rotational kinetic energy for rolling. So one of the things that you might have picked up on is that rolling objects have to be able to stick or have static friction, or they would slide, right? If they didn't have static friction, then they wouldn't roll, they would slide. So we take a quick look at this, and we see that the point in contact will always have a frictional force that resists motion, right? But that is a static friction. There is no sliding. Remember, this is rolling without sliding. And that means that since there is no force acting over a distance, static friction is for objects that are not displaced. That means that the work done by static friction will always be zero. There will never be work done by static friction. So that means that rolling objects don't go slower because of friction. That's a common misconception. They just go slower because there's some amount of the potential energy at the top that gets converted into rotational energy, and therefore is not available for linear kinetic energy. So we've looked at how to calculate kinetic energy. Now let's look at work done on rotational objects by torque. It's a pretty straightforward idea, and that idea is that work equals force times distance, right? And here the work would be a force, F, applied over a distance, right? And that distance is just some arc length. Sorry, I'll let that clear up. Right? So the work done by torque, right, torque is the radius times the force. The work done by torque would be the force times some change in position at work equals force times distance. But we know that there's a relationship between the distance that the force was applied and the translational values theta and r. So what we can do is we can replace delta L with work equals force times distance equals force times radius times the change in the radians. So that means that since Fr equals torque, I can replace in the rotational work equation is work equals torque times the change in radians. And if this is work and power is work over time, then power is also torque times change in displacement divided by time. And change in displacement over time, it would be the rotational velocity. So that means that power is work over time, which we could calculate with rotational values, or that power equals torque times angular velocity. So that sums up our conservation of energy and our rotational kinetic energy, which leaves us just one concept left, and that is rotational momentum.